What if the quiet hand of the sun has been shaping us in ways we rarely notice, not only as the giver of light and warmth but also as a slow and steady influence on the very path of human evolution? To imagine this, we need to step back in time and scale, to think not in days or seasons, but in cycles that last thousands and even tens of thousands of years. The sun is not a constant lamp. It pulses gently, its activity rising and falling like a slow tide. Every 11 years or so it reaches a peak of storms and flares, and then it calms again. Over even longer spans its patterns shift more deeply, sometimes quieting for centuries, sometimes becoming more restless. For life on Earth, these rhythms are like distant background music, faint yet persistent. The sun's energy does more than warm the ground. It also influences the atmosphere, the winds, and the subtle balance of climate. When activity is high, the solar wind, streams of charged particles, grows stronger, shaping how much cosmic radiation reaches us. This invisible radiation, when it slips through, can cause tiny changes in DNA, a process we call mutation. Mutations are the raw material of evolution, small changes in the code of life. Most are neutral, some harmful, and a few helpful, depending on context. It is possible, though not certain, that the sun's changing mood may have adjusted the pace of these changes, ever so slightly, across generations. We cannot point to a single mutation and say, this came from the sun. Evidence does not allow for such clarity. Instead, we rely on indirect signals, on the language of traces. Ice cores drilled deep in Greenland and Antarctica hold bubbles of ancient air, tiny time capsules of past climates. In these frozen archives we see patterns that match solar cycles. When the sun was calm, Earth cooled. When it was more active, climates shifted in other ways. Tree rings tell similar stories. In narrow rings formed during hard years and wider rings of easier growth, we find echoes of solar variations. The sun left its mark not on paper, but in wood and ice, in the quiet memory of natural archives. Now let us pause and imagine a thought experiment. Suppose the sun had entered a very long quiet phase while early humans were spreading across Africa. A colder, harsher climate might have slowed migration, concentrating populations in smaller regions. Over thousands of years this could have led to different social structures, different survival strategies, and perhaps different paths of cultural growth. Or imagine the opposite, a prolonged period of higher solar activity, slightly warming northern regions, opening grasslands and routes earlier than they otherwise appeared. Migrations might have unfolded sooner, changing the map of human presence across continents. Neither scenario is provable, yet both remind us how sensitive the balance can be when traced over deep time. The limits of our knowledge are clear. Solar records stretch back reliably only a few centuries. Beyond that we infer, using isotopes like carbon-14 and beryllium-10, which form in the atmosphere when cosmic rays strike. Higher cosmic rays mean a quieter sun, lower rays mean a stronger solar shield. These isotopes accumulate in tree rings and ice, offering a coded diary of solar moods across tens of thousands of years. When we read them, patterns appear. Yet interpretation is delicate. Other factors, like volcanic eruptions, also shape climate and isotope levels. Distinguishing the sun's whisper from Earth's own voice is not easy. Still, the resonance is there, quiet but persistent. For human evolution, this means that we must think not in single events, but in slow pressures, gentle nudges. Climate stress can favor adaptability. Groups that endure shifting environments may pass on not only genes but also cultural habits of flexibility, of resilience. In this way, even if the sun influenced only the background climate, it may have indirectly influenced the pathways humans explored, the tools they invented, and the migrations they undertook. Now we can soften into a pause. The sun remains a star, vast and distant, yet also intimate. It touches every day of our lives. Whether or not its cycles nudged our genetic story directly, its rhythms certainly shaped the landscapes we inhabited. To think of human evolution without the sun is impossible. To imagine it shaped by the sun in ways we cannot fully prove is a quiet reminder of how connected we are to forces larger than ourselves. And so we leave the question open, resting in the uncertainty, allowing the thought to linger like evening light fading across a horizon. What if our evolution was never a closed story of Earth alone, but always part of a larger neighborhood, where silent visitors from space left their traces on the path of life? To think about this, we can imagine the solar system not as empty blackness but as a wide landscape, filled with drifting objects, streams of dust, and long journeys of comets and asteroids. These neighbors are not distant abstractions. They sometimes cross our path, leaving marks in ways subtle and direct. A comet is a body of ice and dust, a frozen traveler from the outer reaches. When it approaches the sun, its surface warms and releases gas, forming the glowing tails we see in the night sky. Asteroids are rocky, remnants of early planetary building blocks. They travel mostly between Mars and Jupiter, but some wander closer. Over time, Earth encounters fragments of both. Most are small and burn up in the atmosphere, appearing as quiet streaks of light we call shooting stars. Yet even in burning, they leave behind fine dust, settling slowly across land and sea, a thin rain of material not born on Earth. Every year, tons of this cosmic dust accumulate, unnoticed by us yet steady, a faint but constant exchange between planet and sky. Larger objects make deeper impressions. A meteorite that survives its fall becomes a physical reminder, a piece of the wider solar system resting on our soil. Some carry rare metals, some even complex organic molecules, the chemical building blocks of life. It is possible that such deliveries, happening countless times across billions of years, enriched Earth's inventory, adding ingredients that later became part of living systems. But we must be careful here. We cannot prove that human evolution depended on these contributions. Evidence does not allow such precision. Instead, we work with probabilities, with patterns, with the quiet records left in archives of stone and ice. Sediments at the bottom of oceans contain layers of dust that can be traced back to cosmic sources. These layers act like calendars, showing times of increased input, perhaps when Earth crossed through dense streams left behind by comets. Ice cores, too, hold tiny fragments, preserving a memory of what once drifted down through the atmosphere. These are the indirect signals, the language of traces. Craters are another form of record. Each large impact reshaped landscapes, ecosystems, and opportunities for life. Not all were catastrophic, though the most famous ones did cause mass extinctions. Many were smaller, local, influencing climate and migration routes only subtly. Over millions of years, such events became part of the background shaping of evolution. Now let us linger with a thought experiment. Imagine a comet delivering a steady rain of organic-rich dust over tens of thousands of years. In shallow ponds and soils, these molecules might interact with existing chemistry, slightly shifting the pathways of early life. If even one small process of replication or stability was altered, the chain of events leading to complex organisms could have changed. Later, imagine a modest asteroid impact in Africa during the rise of early hominins. Not large enough to destroy ecosystems, but sufficient to alter rainfall patterns for centuries. Populations would have adapted, perhaps moving into new valleys or experimenting with new food sources. Such movements could have influenced which groups survived, which learned to cooperate differently, and which carried certain genetic variations forward. In this way, cosmic neighbors may have played a quiet, guiding role, not by design but simply by presence. The limits of our understanding remain wide. We cannot rewind the story to see exactly what changed because of these encounters. The evidence is indirect, pieced together from scattered markers. Absence of proof is not proof of absence, and so we proceed with caution, acknowledging uncertainty as part of the narrative. Yet the persistence of the traces suggests we cannot exclude these influences entirely. For us, it is enough to hold the idea gently, that our story is not only written by rivers and forests, but also by comets and stones from the dark. The solar system is not a distant stage but part of the home where life unfolded. When we think of human evolution within this larger frame, we are reminded that Earth has always been porous, open to exchange, quietly shaped by the company it keeps. And so we let the thought rest, like dust settling through air, light and silent, becoming part of the ground beneath us. What if the slow breathing of the sun, its cycles of activity and rest, quietly shaped the conditions in which human ancestors lived and adapted? To think of this, we need to stretch our sense of time beyond lifetimes, beyond recorded history, into spans of centuries and millennia, where patterns emerge that are too wide for any one generation to notice. The sun is not still. It flickers with rhythms. Every 11 years, on average, it moves from calmness to storminess and back again. At times, its surface erupts with dark sunspots and flares, sending waves of energy outward. At other times, it is quieter, almost serene. These shifts influence the flow of solar wind, streams of charged particles moving through space. When the solar wind is strong, it shields Earth more effectively from cosmic rays, high-energy particles arriving from beyond the solar system. When the wind is weaker, more of these rays reach our atmosphere. This balance matters. Cosmic rays, when they collide with molecules in the air, can produce secondary particles that reach the surface. Some scientists propose that over long stretches, this could influence mutation rates in living organisms. Mutation, in simple terms, is a small change in DNA, the code of life. Most mutations are like spelling variations in a long book. Many have little effect, some disrupt meaning, and a few create new possibilities. Evolution depends on such changes. If solar cycles gently adjusted how many of these changes occurred, even slightly, then over thousands of generations the cumulative effect could be real. We must be cautious here. No direct evidence ties a particular solar storm or a quiet century to a specific human genetic change. The links are indirect, filtered through layers of climate, environment, and probability. Absence of direct proof does not mean absence of influence. Instead, we look for the language of traces, signals preserved in natural archives. Ice cores, drilled deep in Greenland or Antarctica, reveal patterns in trapped air and isotopes. When cosmic rays increase, isotopes like beryllium-10 form more abundantly in the atmosphere and become locked into snow and ice. These variations, read like subtle lines on a frozen page, align with known solar cycles. Tree rings offer another diary. In years of lower solar activity, more cosmic rays penetrate, altering carbon-14 levels in the atmosphere. Trees absorb this carbon as they grow, leaving behind a record of solar mood written in wood. These signals stretch back thousands of years, long before telescopes, giving us glimpses of the sun's longer rhythms, like the Maunder Minimum, a period of deep quiet between the 1600s and 1700s, when sunspots nearly vanished. During that time, Europe and parts of the world experienced colder winters, rivers freezing in ways rarely seen before or since. Now let us imagine carefully. Suppose early humans lived during a prolonged calm period of the sun, when more cosmic rays reached Earth, slightly raising mutation rates. Over countless births and lifetimes, the genetic variety in those populations might have been greater. This could have provided more material for natural selection to work with, more diversity of traits to test against changing climates. On the other hand, imagine a long stretch of stronger solar activity, with fewer cosmic rays penetrating. Mutation rates might have slowed slightly, making populations more stable, less varied, perhaps better suited to a steady environment. Over long spans, even small differences in the pace of change could ripple outward, shaping the flexibility of human groups in ways we cannot measure directly. The limits of our understanding are firm. Solar records extend only so far, and many influences overlap. Volcanic eruptions, shifts in ocean currents, orbital variations of Earth itself, all play roles in climate and habitability. Distinguishing the sun's subtle whisper from these other voices is complex. Still, the correspondence of signals across ice, wood, and sediment suggests that the sun's cycles are not just distant phenomena, but part of the environment to which life has always responded. For human evolution, the implication is gentle but profound. Even if we cannot link specific genetic shifts to solar patterns, we can say with care that the sun shaped climates, resources, and challenges our ancestors faced. It set the stage upon which adaptation unfolded. Its presence is not only in light and warmth, but also in rhythms we may only now be beginning to trace. And so we rest with this thought: the sun as a companion, not just overhead, but woven into the story of life itself. Its cycles may have touched us quietly, invisibly, over deep time. Whether that touch was decisive or only marginal remains uncertain. The truth is likely both smaller and larger than we imagine, smaller in direct effect, larger in context. We let this possibility linger, like a soft echo fading into silence, holding space for the unknown. What if the invisible showers of cosmic rays, endlessly arriving from the depths of space, played a quiet role in the shaping of our lineage? To approach this thought, we need to expand our vision beyond the warmth of the sun, out to the vast fields between stars, where energetic particles are born. They come from violent places, supernovae, the explosive deaths of stars, and even more distant and mysterious sources. By the time they reach us, they are no longer a storm but a fine, unseen rain, falling without pause upon Earth. We cannot see them with our eyes. A cosmic ray is simply a charged particle, often a proton, moving at almost the speed of light. When it collides with the atmosphere, it creates a cascade, secondary particles scattering down like a quiet spray. Some reach the ground. Some pass through us without notice, like shadows that leave no immediate mark. Yet on the smallest scale, these encounters can affect the delicate fabric of DNA. A stray particle may nudge a genetic sequence, changing one letter in a vast book. Most such changes are harmless, some are harmful, and a rare few may contribute to adaptation. Evolution depends on these small steps, and so even a faint rain, constant over millions of years, may have left its imprint. Now we can pause and consider the scale. Cosmic rays are not unique to one era. They have always been with us. The atmosphere and Earth's magnetic field shield us from the majority, but their intensity still varies. When the sun is active, its strong wind pushes many of these particles aside, lowering the dose that reaches Earth. When the sun is calm, more pass through. The galaxy, too, has rhythms. As the solar system drifts through spiral arms, regions dense with stars, the background of cosmic rays may increase. Over spans of tens of millions of years, Earth's exposure changes as we orbit the center of the galaxy. These cycles are far too long for a human to feel, but across evolutionary time, they may matter. The challenge is evidence. We cannot trace a single human trait to a cosmic ray. Instead, we turn to isotopes, special forms of atoms created when cosmic rays strike the atmosphere. Carbon-14, for example, forms in this way, and its presence in organic material lets us date once living things. Beryllium-10 is another marker, found in ice cores, its concentration rising and falling with cosmic ray intensity. These are the quiet footprints left in natural archives, signals that allow us to glimpse the flow of particles long after they have passed. Reading them is like listening to echoes in a cave, faint, indirect, but telling. Now let us linger with a thought experiment. Suppose a period of high cosmic ray flux occurred during a crucial phase of early human evolution. More mutations might have arisen, most unnoticed, but a few beneficial ones spreading through populations over generations. Perhaps these changes gave certain groups a slightly better chance in shifting climates, or a new way of processing food, or even subtle differences in brain wiring that supported cooperation. Then imagine a contrasting period, when cosmic rays were shielded by strong solar winds. Fewer mutations occurred, populations stabilized, changes slowed. Over many millennia, the rhythm of adaptation itself could have pulsed gently with the sky. We must remain cautious. Evolution is complex, shaped by many overlapping factors: environment, chance, migration, catastrophe, and survival. To separate out the contribution of cosmic rays is nearly impossible. Absence of direct proof does not mean absence of influence, but neither does possibility guarantee importance. What we can say is that the quiet rain is real, the traces measurable, the timing aligned with larger cosmic patterns. This awareness places us in context. Our DNA is not sealed away from the universe. It has always been open, not only to the pressures of earthly life but also to the faint signatures of distant stars. Now, as we let this thought settle, we can soften into perspective. Perhaps the role of cosmic rays was small. Perhaps it was greater. The truth likely lies somewhere in between, its details hidden in the long memory of time. For us, it is enough to acknowledge that human evolution unfolded under a sky that was never silent, touched not only by sunlight but also by invisible messengers from far beyond. What if the stones that fall from the sky, the meteorites, were not only silent visitors but also subtle messengers, bringing with them material that may have nudged the course of life on Earth? To explore this, we can imagine our planet not as an isolated island but as a shore along which waves of cosmic matter sometimes wash up. Most of the time these waves are small, grains of dust that settle invisibly through the atmosphere. Yet sometimes larger fragments arrive, surviving the long descent and resting on the ground as heavy, otherworldly rocks. A meteorite is simply a fragment of an asteroid or a comet that has reached Earth's surface. When we hold one in our hands, we are holding something older than our planet itself, material left over from the early building of the solar system. Some carry rare metals like nickel and iridium. Others contain complex organic molecules, carbon-based compounds that form the foundation of life. Their presence in meteorites does not prove that life came from space, but it shows that the chemistry of life is not unique to Earth. Ingredients are scattered widely, waiting for the right conditions to combine. Now let us gently consider mechanisms. When meteorites strike, they deliver more than their contents. The energy of impact can alter landscapes, creating craters, stirring dust, and changing climates for years. Large impacts are rare but profound. Smaller ones are frequent, sometimes unnoticed, yet over long spans they accumulate, each adding a subtle mark to Earth's record. The question of influence on human evolution lies not only in catastrophic events but also in the quieter possibilities of enrichment. If meteorites supplied extra molecules or minerals, they could have become part of early biological processes, long before humans appeared. Later, in the hands of our ancestors, iron from meteorites became one of the first metals shaped into tools, long before smelting was invented. A piece of sky iron, hammered into a blade, is both artifact and testimony, bridging human ingenuity with cosmic material. The evidence for these ideas lies in traces, not in direct connections. Layers of clay enriched with iridium point to ancient impacts, like the one that ended the reign of the dinosaurs. Tiny spherules and sediments mark the spray of melted rock from collisions. Meteorites themselves, studied in laboratories, reveal amino acids, complex molecules that hint at chemical richness delivered from beyond. None of these prove a direct line to human evolution, but together they suggest openness. Earth has always been receiving, not only from its own processes but from the cosmos around it. Now we pause with a thought experiment. Imagine a steady rain of meteorites delivering organic molecules over millions of years. In shallow waters, these compounds mix with Earth's own chemistry. Some combinations fail, others persist. Over time, the chemical diversity increases, making it more likely that self-replicating systems emerge. This does not mean life was imported, but perhaps it was encouraged, enriched, given more pieces with which to build. Later in time, imagine early humans encountering meteorites scattered across plains. Unlike ordinary stones, these are heavier, denser, and sometimes metallic. A curious mind might notice their unusual qualities. A fragment hammered into shape becomes a sharp tool, stronger than bone or wood. In this way, meteorites enter the human story not through biology but through culture, accelerating the development of technology. The boundaries of our knowledge remain. We cannot measure precisely how much organic material meteorites contributed compared to Earth's own chemistry. We cannot prove that any one object changed the course of life. Yet the traces are real: isotopes in soil, molecules in stones, scars in landscapes. The absence of certainty does not erase the possibility of influence. Instead, it leaves us with a perspective of connection, of Earth as part of a larger system of exchange. And so we let the thought rest quietly. Meteorites may have been messengers, sometimes catastrophic, sometimes generous, always present across the deep time of evolution. They remind us that even the ground beneath our feet holds stories from the stars, and that our human journey may have been touched, however lightly, by matter that once wandered far beyond our sky. What if the scars left by ancient impacts, the craters that still mark Earth's surface, are not only reminders of destruction but also quiet witnesses to the turning points of evolution. To enter this thought, we must widen our perspective to spans of millions of years, where single collisions reshape ecosystems, redirect climates, and open spaces for new forms of life. A crater is more than a hollow in stone. It is the record of a sudden meeting between Earth and a body from space, an asteroid or a comet fragment carrying immense energy. In the moment of impact, landscapes are transformed, rock melts, shockwaves spread, dust rises into the sky. For days or months, sunlight may dim, temperatures may fall, food chains may strain. For decades or centuries, the effects ripple outward. Yet over longer stretches, these disruptions create new ecological openings. Species vanish, and others, often smaller and more adaptable, move in to fill the spaces left behind. Evolution rarely happens in straight lines. It moves in fits and starts, with long periods of stability and sudden changes. Impacts may have been among the triggers for these sudden shifts. Now we pause on the scale of evidence. Many ancient craters have been erased by erosion, covered by forests, or hidden under oceans. Still, some remain. The Chicxulub crater in Mexico, over 180 kilometers wide, tells of the impact that coincided with the end of the dinosaurs around 66 million years ago. In sediments from that time, a thin layer enriched with iridium, a rare element more common in meteorites than in Earth's crust, marks the event like a bookmark in the planet's history. Other craters, smaller and less famous, dot the continents. Each is a reminder that the surface we walk on is not only shaped by Earth itself but also by encounters with the wider solar system. The language of traces extends beyond craters. Spherules of glassy rock, formed when molten material cooled and fell back to Earth, are found in ancient sediments. Shocked quartz, a mineral structure altered by intense pressure, remains as a microscopic signature of impacts. These quiet clues, spread across layers of stone, allow us to piece together the hidden record of cosmic collisions. For human evolution, the connections are indirect but worth considering. Large impacts reshaped climates and ecosystems long before our species appeared. Yet the patterns they set in motion influenced which lineages survived and which vanished, shaping the branches of the evolutionary tree that eventually led to us. Now let us imagine a thought experiment. Suppose a medium-sized impact occurred during a critical period of early human development, perhaps 2 million years ago. Not large enough to cause mass extinction, but sufficient to alter rainfall patterns for centuries. Grasslands dry, forests thin, rivers change course. Populations of early hominins, facing shifting landscapes, adapt by traveling farther, experimenting with new foods, developing more flexible social structures. A small environmental pressure, extended over time, nudges the trajectory of adaptation. Or imagine an impact in a distant region, altering climates half a world away. A cooling event pushes animal herds into new territories. Human ancestors follow, encountering new challenges, predators, and opportunities. The story is not one of a single event but of chains of cause and effect, rippling through time. The limits of our knowledge remain. We cannot link specific human traits to specific craters. The archives are partial, the signals overlapping with other influences such as volcanic eruptions and orbital shifts of the planet. Absence of precise links does not erase the likelihood of influence. It only reminds us of the humility required when we look into deep time. And so we arrive at a gentle conclusion. Craters are scars, yes, but they are also chapters in the story of life. They show us that Earth is not closed, that evolution unfolds in a context of exchange with the wider solar system. For humans, the role of impacts may have been indirect, filtered through ecosystems and climates, but real nonetheless. To walk across a landscape shaped by such an event is to move through a silent memory, a reminder that our story is written not only in soil and bone but also in stone and sky. What if Earth's magnetic field, invisible yet ever-present, played a quiet role in guiding the conditions under which human evolution unfolded? To think of this, we need to imagine a vast shield surrounding our planet, a field shaped by the slow churning of molten iron in Earth's outer core. Like a protective cocoon, It bends and redirects much of the charged radiation streaming from the sun and from distant stars. Without it, the atmosphere would be more exposed, the surface more fragile. The field is not fixed. It shifts slowly over time, drifting in strength and even reversing its poles, when north becomes south and south becomes north. These reversals happen irregularly, across spans of hundreds of thousands of years. During such times, the field weakens, allowing more cosmic rays and solar particles to reach the atmosphere. For us, the presence of this shield is something we rarely notice, but for life over geological time, its role may have been steady and important. Now we pause to consider the mechanisms. Charged particles from space can interact with the atmosphere, producing showers of secondary particles, increasing radiation levels on the ground. Most of the time, the field deflects them. When it weakens, more arrive. Over long periods, this could mean subtle shifts in mutation rates, as DNA becomes slightly more exposed to radiation. It could also mean changes in climate, since particles in the upper atmosphere may influence cloud formation. The evidence is indirect. We do not have a fossil record of magnetic fields, but we do have rocks. When lava cools, iron-rich minerals align with the direction of the magnetic field at that moment. These alignments are preserved, like compass needles frozen in stone. By studying layers of volcanic rock or sediments, scientists reconstruct the history of field reversals. In the seafloor, stripes of magnetized rock mirror the flip-flop of polarity, creating a barcode of Earth's magnetic memory. This is the language of traces, quiet yet durable. Now let us linger with a thought experiment. Imagine a period when the field was weak, letting more radiation through. Early human populations, small and scattered, might have faced slightly higher mutation rates. Most changes would be unnoticed, but over generations, this could lead to more variation, more diversity of traits. Some traits might help survival in new climates or landscapes. Others would fade away. Later, when the field strengthened again, the pace of mutation slowed, stabilizing populations for long intervals. In this way, the rhythm of reversals could have been a subtle metronome, influencing the tempo of evolutionary change. We cannot prove this with certainty. The timing of reversals is known, but linking them directly to evolutionary events remains difficult. Many other factors overlap: climate shifts, tectonic changes, asteroid impacts. Separating the voice of the magnetic field from this chorus is not easy. Absence of direct evidence does not mean absence of influence. Instead, it reminds us to approach with humility, acknowledging the limits of what we can know. And yet, when we think of the field's protective role, its presence feels essential. Without it, Earth might have lost much of its atmosphere, stripped away by solar wind, as happened on Mars. Life here may have struggled to flourish in the same way. For humans, even if reversals only played a modest role, the shield itself has been a quiet guardian, holding open the conditions that allowed our story to unfold. Now we soften into perspective. The magnetic field is a reminder that forces we cannot see still shape our world. Its lines curve around us constantly, unbroken, unspoken. Whether a shield, metronome, or gentle filter, it remains part of the background of human history. We rest with this thought: evolution was never only about what happened on Earth's surface, but also about the unseen fields that surrounded us, guiding the balance between Earth and sky. What if the moon, our quiet companion in the sky, has been more than a distant light and instead a steady influence on the story of human evolution? To hold this thought, we need to imagine the moon not as a decoration above us, but as a constant presence shaping the rhythms of Earth itself. Its gravity pulls on oceans, creating tides that rise and fall in regular patterns. These tides, small on a daily scale, have been enormous in shaping life over geological time. In shallow coastal zones, tides alternately expose and cover land. Early life forms, long before humans, adapted to this pulsing environment. Some learned to survive in water, some on land, and some in between. This constant movement may have encouraged flexibility, creating the conditions for species to explore new niches. When we think of human ancestors, we remember that they too lived near rivers, lakes, and coasts, drawn to places where water met land. The moon's steady pull guided these environments, influencing the resources available and the migrations that followed. Now let us pause with the mechanism. The moon stabilizes Earth's tilt, keeping our seasons more regular. Without it, the tilt might have wandered chaotically, creating unpredictable climates. Instead, our planet has known cycles, sometimes colder, sometimes warmer, but within ranges that life could adapt to. Human evolution unfolded in this relative stability, shaped by the predictable rhythm of seasons. It is difficult to imagine our ancestors developing in a world where summers might vanish for millennia or winters stretch unpredictably. The moon's silent balancing hand may have prevented such chaos. The evidence for these influences is indirect. Geological records show regular cycles of tides stretching back through time. Fossil corals and shells contain growth lines, much like tree rings, that revealed the changing length of days and months over millions of years. These tiny archives show that the moon has been gradually moving away from Earth, lengthening our days, softening the speed of tides. The rhythm we know now is only the current chapter of a long unfolding story. The language of traces is also cultural. Humans have long measured time by the moon's cycles, from the waxing crescent to the full circle of light. Calendars, rituals, and journeys were tied to this rhythm. Even if indirect, the moon shaped human behavior, binding our awareness of time to its phases. Now let us rest with a thought experiment. Imagine Earth without the moon. The tilt of our axis shifts unpredictably. Sometimes the poles lean steeply, creating extreme seasons. At other times the axis lies almost flat, erasing much of seasonal variation. Populations of early humans, facing climates that swing wildly, may have struggled to survive. Migrations would have been forced by sudden cold or heat. Culture might have developed differently, focused on constant adaptation rather than stability. Or imagine instead a closer moon, tides rising higher, flooding vast coastal plains each day. Early humans living near shores would have been shaped by this rhythm, perhaps becoming even more dependent on the sea, inventing ways to move with tides, creating technologies sooner to bridge land and water. These scenarios are speculative, but they help us sense how deeply the moon's presence matters. The limits of knowledge remind us to be cautious. We cannot link a single trait in human evolution to a tidal cycle or a stable tilt. Too many other forces overlap: volcanoes, orbital shifts, impacts from space. Still, the traces in geology, in fossils, and in culture together suggest that the moon is not just background. It is woven into the conditions that allowed life, and humans within it, to flourish. And so we let this thought settle. The moon remains above us, quiet and steady, pulling oceans, balancing seasons, marking time. Whether or not it directly shaped our genes, it shaped the stage on which our story unfolded. To walk along a shore at low tide is to touch a rhythm older than humanity, a rhythm set by our nearest cosmic neighbor. What if the slow cycles of Earth's orbit, the gentle variations in tilt and path around the sun, played a hidden role in shaping the conditions where human ancestors lived and adapted? To approach this idea, we need to think in spans far beyond the rhythm of seasons, even beyond the centuries of recorded history. These cycles, known as Milankovitch cycles, unfold over tens of thousands to hundreds of thousands of years. They are not sudden shifts, but gradual drifts, like the slow breathing of the planet in relation to the sun. The tilt of Earth's axis changes slightly over time. Sometimes it leans a little more, making seasons more extreme, with hotter summers and colder winters. At other times it leans less, softening the differences. The shape of Earth's orbit also varies, stretching into a more elongated oval or returning to a nearly perfect circle. A third rhythm, called precession, is a slow wobble of the axis, like a spinning top that does not stand perfectly still. Together, these cycles alter how sunlight is distributed across the planet. They do not change the total energy we receive, but they shift where and when it arrives. Over long stretches, these small changes are enough to tip Earth in and out of ice ages. Now we pause to consider what this means for human evolution. Our earliest ancestors lived through repeated ice advances and retreats, landscapes reshaping slowly around them. Forests expanded, then shrank. Grasslands grew wide, then gave way again. Rivers shifted courses. In these changing environments, humans did not remain still. Populations moved, adapted diets, adjusted tools, and developed strategies for survival. Climate stress may have encouraged flexibility, cooperation, and migration, qualities that became part of our story. The traces of these cycles are preserved in archives of ice and sediment. Ice cores from Greenland and Antarctica hold layers of ancient snow, each year adding a page to a frozen book. Within them are bubbles of trapped air, tiny time capsules of past atmospheres. Levels of carbon dioxide and oxygen isotopes within these bubbles reveal the waxing and waning of ice ages, matching the rhythm of orbital cycles. Ocean sediments carry similar records. Tiny shells of microorganisms sink and accumulate over millions of years. Their chemical composition reflects the climate of their time. By reading these shells, scientists reconstruct the pulse of ancient temperatures, again finding the signature of Milankovitch cycles. These are the indirect signals, the quiet footprints of orbital changes across deep time. Now let us imagine a thought experiment. Suppose Earth entered a long cold phase, ice sheets advancing across continents. Human ancestors living in Africa or Eurasia might face shrinking resources. Some groups migrate, seeking warmer regions. Others remain, adapting to harsher conditions. Over thousands of years, these pressures shape differences in survival strategies, in body forms, in cultural habits. Later, as the orbit shifts and climates warm again, new opportunities arise. Forests spread, animals return, and humans follow. Each cycle nudges populations, not by force but by persistence. The pace is slow, yet the influence accumulates. The limits of our knowledge are clear. Climate is complex, shaped not only by orbital cycles but also by volcanic activity, solar variations, ocean currents, and even chance events like impacts. To say that human evolution was guided only by these cycles would be an overstatement. Yet to ignore them would also miss something important. They form the backdrop, the stage upon which other events played out. And so we arrive at a gentle conclusion. The slow drift of Earth's orbit, invisible on the scale of days, became a quiet rhythm guiding the dance of ice and warmth, scarcity and abundance. Humans, like all life, moved to this rhythm, adjusting without awareness of its source. The cycles continue still, slow and steady, reminders that our story is tied not only to the land beneath us but also to the paths our planet traces through space. We let this thought rest, like a faint echo stretched across deep time, shaping us without our knowing. What if the fine dust drifting through the galaxy, tiny grains from stars long gone, has quietly touched Earth and left traces in the background of our evolutionary story? To hold this thought, we need to expand our sense of space beyond the solar system and imagine the interstellar medium, a vast and almost empty sea where even the smallest particles travel slowly across light years. This dust is not like the dust we sweep from a table. Each grain is a fragment of a larger story, atoms forged in the hearts of stars, carried outward by explosions, wandering through space until, by chance, some enter our solar system. Earth, moving in its orbit, occasionally passes through regions where this dust is denser. The particles slip into the atmosphere, some burning as faint meteors, others settling silently onto oceans and land. Over years, this contribution is small, almost invisible. Over millions of years, it becomes measurable, an accumulation written into sediments and ice. Now let us pause with the mechanism. Interstellar dust carries isotopes, special forms of atoms, that can act as markers. One example is iron-60, a rare isotope produced in supernovae. It does not occur naturally on Earth in significant amounts, so when we find traces of it in ocean sediments, it signals a delivery from beyond. These findings suggest that sometime in the last few million years, Earth passed through clouds of material enriched by nearby stellar explosions. The evidence is delicate, but persistent, recorded in layers of seabed like fine handwriting in stone. For human evolution, the link is indirect. Such dust is not known to alter DNA directly. Its influence is more likely environmental, perhaps through small changes in climate or chemistry. A steady influx of particles could alter atmospheric processes, affecting cloud formation or rainfall. Over long timescales, Even subtle shifts in climate may have guided migrations, food availability, and adaptation. The challenge is limits. We cannot say exactly how much dust arrived, or what its precise effects were. The signals are faint, and they overlap with many other influences: volcanoes, solar cycles, orbital changes. Absence of clarity does not erase the possibility. Instead, it reminds us that evolution unfolds within a web of many causes, some close, some unimaginably far. Now let us linger with a thought experiment. Imagine Earth moving through a denser interstellar cloud for several thousand years. More dust enters the atmosphere. Sunlight dims slightly, perhaps by only a fraction of a percent, but enough to cool climates. Glaciers advance. Populations of early humans, already living at the edge of survival, face new challenges. Some move south, others adapt with new strategies, perhaps developing tools or social structures that give them resilience. Then, after centuries, Earth leaves the cloud. The skies clear, climates ease, but the adaptations remain, carried forward by the generations that endured. Or imagine a gentler scenario. Dust rich in rare isotopes falls into the oceans, slightly changing chemical balances. Microorganisms respond, shifting the base of the food chain. Over time, these small changes ripple upward, influencing larger ecosystems. Human ancestors, relying on these ecosystems, experience subtle but lasting pressures. These are only possibilities, not certainties. The truth may be smaller, or larger, or different entirely. What remains certain is that interstellar dust leaves its language of traces: iron-60 in sediments, isotopes in Antarctic snow, quiet markers of encounters with the galaxy itself. And so we soften into perspective. Earth is not sealed away from its surroundings. Our planet drifts through space, open to encounters, touched even by particles born in the death of stars. Human evolution, shaped by many forces, may carry within it faint echoes of this cosmic dust. Whether the influence was decisive or only marginal, we cannot yet know. But the presence of these traces reminds us that our story has always been part of a larger one, written across scales far beyond the human eye. We let this thought rest gently, like dust settling through air, unnoticed yet persistent, part of the ground beneath our feet. What if the distant explosions of stars, the great supernovae, reached across space and left quiet marks on Earth, shaping conditions in which human ancestors evolved? To imagine this, we need to step into scales larger than our planet, into the life cycle of stars themselves. A supernova is the death of a massive star. When its fuel is exhausted, it collapses inward, then rebounds outward in a colossal release of energy. For a moment, it can outshine an entire galaxy. Waves of particles and radiation spill into surrounding space, carrying the ashes of the star, newly forged elements, rare isotopes, fragments of matter that will drift for millions of years. By the time these signals reach Earth, they are no longer a bright flare but a subtle rain, sometimes leaving measurable traces. The atmosphere and magnetic field protect us from the worst of this energy, yet the influence may still touch climate, chemistry, and even biology. Now let us pause with the mechanism. Supernovae send out cosmic rays, high-energy particles moving at near light speed. When Earth passes through their lingering clouds, radiation at the surface may rise. These particles, colliding with our atmosphere, create isotopes such as iron-60, which is not produced naturally on Earth in significant amounts. Finding it in ocean sediments or Antarctic snow is like finding an unfamiliar signature on a familiar page. It tells us that at some point in the last few million years, nearby stars ended their lives and their echoes reached us. The distances are vast, yet the marks are preserved. For human evolution, the link is indirect, filtered through climate and ecosystems. Increased radiation might have nudged mutation rates slightly, adding more variation to populations. Dust from such explosions, drifting into our solar system, could have shaded sunlight a little, cooling climates, shifting rainfall. These changes may have altered habitats, challenging early humans to move, adapt, and find new strategies. Now we turn briefly to evidence. In layers of seafloor sediments, scientists have identified deposits of iron-60 dated to a few million years ago. These coincide with times when hominin species were diversifying in Africa. The connection is not causal by proof, only suggestive by timing. Absence of direct links does not erase the possibility of influence. It only reminds us that many forces overlap in the shaping of life. The language of traces, in this case, is isotopes, atoms carrying memory of distant explosions. Now let us linger with a thought experiment. Suppose a nearby star exploded 2 million years ago, sending a wave of particles toward Earth. For centuries, cosmic rays increased, raising background radiation levels. In small ways, this may have influenced mutation rates in early humans, creating more genetic variety. Most changes vanish, but a few bring subtle advantages, sharper perception, better endurance, or new patterns of social behavior. Over thousands of generations, these traits spread, not because of the explosion itself, but because of the survival that followed. Or imagine another outcome: dust from a supernova drifts into the solar system, dimming sunlight for centuries. Africa's climate cools slightly, grasslands spread wider. Early humans, once tied to forests, are nudged into open landscapes, where upright walking and tool use become more essential. In both cases, the star does not shape humans directly but adjusts the conditions in which choices and adaptations unfold. The limits remain wide. We cannot know the exact distance of past supernovae or the precise intensity of their effects. Too many variables blur the picture: Earth's orbit, its magnetic shield, its atmosphere. What we hold are fragments, isotopes in stone, patterns in sediments. They do not tell us the whole story, but they whisper of connections beyond Earth. And so we arrive at a gentle resting thought. Human evolution may have carried within it faint echoes of distant star deaths, not as decisive commands but as subtle nudges. The explosions that forged heavy elements, the very iron in our blood, may also have brushed our planet again in later ages, influencing the stage on which our story played. To think of this is to remember scale, that our lives are tied not only to rivers and forests, but also to stars that lived and died long before us. We let this idea settle quietly, like starlight reaching us after a journey of millions of years, soft and almost forgotten, yet still here. What if the deep layers of Earth, the stones and sediments, hold a quiet language that tells us how forces beyond our world touch life and perhaps shape our own path? To stay with this thought, we need to imagine rocks not as still and silent, but as pages of a vast archive, each layer a line written slowly over thousands or millions of years. The surface may change quickly, rivers shift, forests grow, glaciers melt, but the buried layers preserve a memory, durable and precise. Within them, traces of distant events can remain, waiting to be read. Now let us pause with the mechanism. When an asteroid strikes, or when dust from a distant star settles on Earth, tiny fragments of these events can become part of the soil, the clay, or the ocean floor. Elements that are rare on Earth, like iridium, can appear suddenly in higher amounts, forming thin bands across the globe. These bands are often no more than a few millimeters thick, yet they stretch across continents, synchronizing distant sites with the same signature. In this way, a single cosmic event can be recorded in stone, its echo preserved long after the event itself fades. Similarly, isotopes, special forms of atoms, become quiet markers. Carbon-14, beryllium-10, iron-60, each has its own story, each forms under specific conditions. When we find them in unusual amounts, we know that something beyond the ordinary occurred. They are like fingerprints left by distant hands. Reading these signals requires patience. Ice cores, drilled from Greenland or Antarctica, show thin lines of trapped air year by year. Ocean sediments, collected from deep-sea floors, reveal shells of microorganisms carrying the chemistry of their time. Together, they form parallel archives, confirming one another, showing patterns of climate, of impacts, of radiation. These are not loud voices, but whispers layered over ages. Now let us consider the limits. We cannot always separate one cause from another. A spike in iridium may signal an asteroid, but volcanic eruptions can also enrich soils with unusual elements. A cooling climate may follow a supernova's dust cloud, or it may be driven by Earth's own orbital rhythm. The traces do not speak directly. They require interpretation, and interpretation brings uncertainty. Absence of a clear marker does not mean absence of influence, and presence of one does not guarantee a single explanation. Still, when patterns repeat across archives, confidence grows. Let us linger now with a thought experiment. Imagine we walk through a canyon where layers of rock are exposed. Each band is a different shade, a different texture. One thin line, darker and richer in metal, marks the time of an ancient impact. Life above this line is different from life below it. Species disappear, new ones appear. Over millions of years, such a boundary influences who survives, who adapts, who vanishes. Now, imagine a more subtle marker, a shift in isotopes, invisible to the eye but clear in chemical analysis. This shift corresponds to a time of higher radiation, perhaps from a distant supernova. For early human ancestors, this change does not arrive as a single moment but as a slow adjustment in climate, in food sources, in challenges faced. Populations respond quietly, some moving, some altering habits, some developing resilience that will be passed along. The traces are not only physical but also biological, written into the flow of evolution itself. Now we soften into perspective. The language of stone and sediment is not complete. Many pages are missing, eroded, or buried beyond reach. Yet the ones we hold remind us that Earth has always been part of a larger story, touched by the sky as well as by its own restless heart. For us, the lesson is not to seek certainty but to recognize connection. Human evolution unfolded in an environment where the ground beneath our feet carries echoes of impacts, of dust, of radiation. Whether these influences were decisive or only gentle nudges, they remain part of the background of our story. We let this thought rest here, like a fossil pressed into stone, quiet and enduring, reminding us that even silence can hold memory. What if our very genes, the long chains of code within each of us, are quiet archives of encounters between Earth and the wider cosmos? To hold this idea, we need to think of DNA not only as a blueprint for life but also as a layered record of changes across time. Every mutation, every small shift in sequence, is like an entry in a diary written over millions of years. Most of these changes happen randomly, through the ordinary processes of copying and error. Yet some may have been nudged by influences from beyond, by radiation, by particles, by shifts in the environment that forced our ancestors to adapt. The genome does not tell us directly where each change came from, but it carries the evidence of long survival. We can pause here to consider the mechanism. Mutations are changes in the sequence of DNA. Sometimes a single letter in the genetic text is swapped, added, or lost. Most of these do not change much. Some can cause harm, while others, rare and subtle, open new paths. Over generations, natural selection keeps what works and discards what does not. Cosmic rays, radiation from the sun, and particles from distant stars all have the potential to trigger such changes. The protective atmosphere and magnetic field shield much of this influence, but not completely. Over the span of millions of years, even a faint extra pressure may have contributed to the flow of mutations. The challenge lies in evidence. We cannot point to one gene and say, this was shaped by a cosmic ray. The traces are hidden within a web of countless changes. What we can do is observe patterns. Genetic diversity rises and falls with population size, with climate stress, with migration. Sometimes bursts of variation appear in the record, aligned with times when Earth itself was under pressure from changing environments. The genome holds these signals, though it does not explain their causes with certainty. It is a record without a key, waiting for careful interpretation. Now we can linger with a thought experiment. Imagine a period of high cosmic ray flux, perhaps triggered by a nearby stellar event. Over many generations, slightly more mutations occur. Most vanish unnoticed, but a few bring small advantages: better endurance, stronger immunity, sharper memory. These traits spread slowly, not as a sudden leap, but as quiet ripples across populations. Later, imagine a population under environmental stress, perhaps from cooling climates. The genetic variations already present, created over time by chance and by faint cosmic nudges, give some individuals resilience. Those who survive pass on not only their traits but also their capacity to adapt. In this way, the archive of genes becomes not just a record but a reservoir, storing possibilities until conditions call them forth. The limits of our knowledge remain wide. The genome does not reveal the origin of each mutation, only its presence. Other forces, chemistry, chance, Earth's own internal processes, are deeply entangled in the story. We must resist the temptation to claim too much. Absence of direct proof does not mean the influence was absent, but neither does the possibility make it certain. Instead, we remain with probabilities, with subtle hints, with the awareness that our DNA has been open to many forces. Now let us soften into perspective. When we read the genome today, we are looking into a layered history, one that connects us not only to our ancestors but also to the wider environment in which they lived. The fact that we find resilience, adaptability, and diversity within our genes is itself a sign of how many pressures, both earthly and cosmic, have been woven into the story. Whether the cosmos added only a faint touch or something more, the record is there, silent but enduring. And so we rest with this thought: within us are archives as deep as stone and as wide as the sky, written in a language we are only beginning to read. What if the stars themselves, quiet guides across the night sky, played a role in the migrations that shaped human history and, indirectly, our evolution? To imagine this, we must step into long nights before maps, before compasses, before artificial light. For countless generations, the stars were not distant abstractions but familiar markers, steady companions that oriented us in space and time. Their patterns, once learned, became tools. The constellations were like signposts in the sky, helping groups move across wide plains, deserts, and oceans. Early humans did not need to understand astrophysics to recognize that the stars returned in predictable rhythms. The sky became a kind of map, larger than any drawn on stone or paper. Now we pause to consider the mechanism. Human ancestors were migratory, responding to climate shifts, food sources, and the movements of animals. Navigation mattered. Landmarks help in daylight, but at night or in open terrain, the sky offers continuity. The North Star, nearly fixed above the northern horizon, could serve as a reference. The arc of the Milky Way, stretching across the sky, pointed directions. Even the rising and setting of familiar constellations marked the seasons, signaling when to move, when to plant, when to harvest. In this way, the stars were woven into practical survival. We cannot know exactly when humans first relied on celestial patterns, but archaeological hints suggest it reaches far back. Rock carvings and bone markings from tens of thousands of years ago may align with lunar cycles or stellar events. Later, in ancient cultures, we see clear evidence: stone circles aligned to solstices, myths tied to constellations. These are not merely cultural decorations but may reflect much older habits of orientation and memory. Now let us linger with the limits. We cannot say with precision how much the stars influenced specific migrations of early humans. Climate and geography remain the dominant forces. Yet to ignore the sky would be incomplete. Even without clear proof, the persistence of star lore across cultures suggests deep roots. The stars left no fossils, but they left cultural echoes, carried through myth, art, and ritual. This is the language of traces, less material than isotopes or sediments, but still durable, preserved in human memory. Let us now imagine a thought experiment. Picture a group of early humans leaving a familiar valley, pressed by drought. At night, they see familiar constellations, rising in the same direction each season. They follow them, moving steadily across plains, finding water, reaching new lands. Over generations, this habit becomes encoded in oral traditions, guiding others. Later, imagine seafaring communities watching the stars reflected in dark waters. They learn that certain constellations rise above particular horizons, helping them cross vast distances. Without this celestial guidance, their journeys might have been slower, riskier, perhaps delayed by centuries. If migration shaped genetic mixing, then the stars indirectly shape the flow of evolution by helping populations meet, exchange, and grow. We must be cautious with such visions. The role of stars is easier to see in later history than in early prehistory. Yet the principle holds. Humans are sensitive to patterns, and the sky offers some of the most consistent patterns available. Whether for survival, for orientation, or for meaning, the stars provided a framework that extended beyond daily needs. And so we soften into perspective. The stars may not have altered our DNA directly, but they guided our steps, influenced where we went, whom we met, and how we remembered our place in the world. They remain above us still, silent companions, unchanged while everything on earth shifts. To look at them is to share in the same quiet guidance that may have helped our ancestors move across continents. We let this thought rest here, gentle and expansive, like the night sky itself. What if the myths we inherited, the stories of fiery skies and visitors from the heavens, are not only creations of imagination but also faint echoes of real events that touched human lives? To hold this idea, we need to see myth not as fantasy, but as memory, stretched, reshaped, but still connected to what people once witnessed. Long before science, stories were the archive. When something strange appeared in the sky, when a comet flared, or a meteor shower lit the night, communities had no instruments to measure or record. What they had were voices, symbols, and traditions. These became the way unusual events were remembered, passed on, and transformed into meaning. Now let us pause with the mechanism. Myths are collective memory compressed into narrative. They work like cultural fossils, carrying impressions across centuries. A blazing comet, frightening in its suddenness, might become in memory the fire serpent, or sky dragon. A meteorite fall, shattering the night with sound and light, might be told as a god descending, or a messenger from above. Over generations, the original event becomes layered with symbolism, yet the trace of the sky remains. We cannot read myths literally as data, but we can sense patterns. When many cultures, far apart, carry stories of falling fire or celestial visitors, it may reflect the universal experience of watching the sky and its occasional disruptions. Now we can linger with the limits. Myth does not give us precise dates or measurements. It bends with time, shaped by memory and need. One story may merge several events, or one event may give rise to many stories. We cannot draw straight lines between ancient tales and cosmic influences. Yet the persistence of themes, comets as omens, stars that fall, visitors from beyond, suggests that the human mind held on to these impressions for a reason. They were important enough to become part of cultural DNA. Let us imagine a thought experiment. Picture a group of early humans gathered around a fire. Suddenly a bright meteor crosses the sky, brighter than the moon, breaking into fragments. For them, without scientific language, this is not a rock from space but a message. They tell the story to their children, who tell it again, and soon the memory becomes part of ritual. 1,000 years later, a carving on stone shows a figure descending from the heavens. The original meteor is gone, but the trace survives in culture. Now imagine another scene. A comet appears, glowing for weeks. It alters the night, creates unease, perhaps coincides with drought or illness. The link is coincidence, but the story is made, a sky visitor bringing change. Generations later, this becomes a myth of a god who brings punishment or renewal. In both cases, we see how sky events leave cultural sediment, not physical fossils but echoes carried in story. The traces are subtle. Ancient calendars aligned with celestial events show us how deeply the sky was woven into daily life. Rock art and bone carvings may mark lunar cycles, solstices, or stellar positions. In these, we find signals that the sky was not a backdrop but a participant in human life. Myths, though intangible, are part of this record. They are not proof, but they are evidence of influence. Now we soften into perspective. Myths cannot tell us directly how human evolution unfolded. But they remind us that our ancestors lived under skies that sometimes startled, sometimes reassured. The stars, the comets, the meteors, they became part of the framework through which humans made sense of their place. Whether the cosmic events changed genetics or only culture, the stories themselves shaped behavior, guiding decisions, creating bonds, fostering resilience. In that way, myth is also evolution, carry not in DNA but in memory and imagination. And so we let this thought rest. The myths of sky visitors may be whispers of comets, of fireballs, of rare celestial events. They are not reliable archives in the way that ice cores or sediments are, but they are human archives, just as enduring in their own way. They remind us that the cosmos has always been part of our story, both in matter and in meaning. What if the quiet presence of radiation, always surrounding us, has been one of the invisible companions of human evolution? To think about this, we need to imagine radiation not as a sudden force but as a constant background hum, present long before we were here and persisting still. Radiation simply means energy carried by particles or waves. Some comes from Earth itself, from the decay of elements in rocks. Some comes from the sun, in bursts and steady streams. And some arrives from far away, from the wider galaxy, drifting to us across space. Our bodies, our cells, our DNA have always lived within this environment. Most of the time the doses are small, unnoticed, like faint static on a quiet channel. Yet across millions of years, these tiny influences may have left their traces. Now let us pause with the mechanism. Radiation can alter DNA. When a particle passes through a cell, it may break or rearrange the sequence of letters in the code of life. Usually the damage is repaired, and often the change has no effect. But sometimes, rarely, the change persists. If it happens in reproductive cells, it can be passed to the next generation. This is what we call mutation. Mutations are the raw material of evolution. Without them, species would not adapt, would not change. Radiation is not the only source. Errors in copying DNA, chemical influences, and chance also play roles. But radiation has likely contributed, in small but steady ways. The challenge is evidence. We cannot point to a single human trait and say it was created by radiation. The traces are too subtle, too intertwined with other processes. What we do see are patterns. Organisms living at high altitudes, where cosmic radiation is stronger, show adaptations over time. Populations near natural uranium-rich soils have lived for generations within slightly higher backgrounds of radiation. The fact that life persists in such places reminds us that the range of tolerance is broad, and evolution has likely absorbed radiation into its rhythm. These are indirect clues, part of the quiet language of traces. Now let us linger with a thought experiment. Imagine a period when Earth's magnetic field weakens, letting more cosmic radiation reach the surface. For hundreds of generations, mutation rates rise slightly. Most changes vanish unnoticed, but some remain. Perhaps they influence skin pigmentation, or immune response, or metabolism. Over time, these traits spread through groups, carried not because radiation intended it, but because survival favored it. Later, as the field strengthens again, the pace slows. The archive of variation remains, ready to be drawn upon when new challenges appear. Or imagine another path, a local population living near rocks rich in natural radiation. Over centuries, they face small but steady genetic changes. Some harmful, some neutral, some advantageous. Those who carry resilience pass it on, and the community develops subtle genetic traits distinct from others. The landscape and the radiation together leave their imprint, written not in stone but in the genome itself. Now we soften into perspective. Radiation, in its quiet background form, is not an intruder but a condition of life. It has been present since the beginning, when Earth was young and when the universe itself was brighter with radioactive heat. Its influence is not clear-cut, not dramatic, but likely continuous. It shaped possibilities without dictating outcomes, one of many overlapping forces guiding evolution. The limits of our understanding remain wide. We cannot measure exactly how much radiation influenced the human line. Yet the awareness that it was always present, always a faint hum in the background, gives us another way to see our connection with the cosmos. We are not separate from these invisible streams. We grew within them. And so we let this thought rest quietly. Radiation, silent and unseen, may have been both a challenge and a gift, shaping the texture of variation upon which natural selection worked. It remains with us still, part of the air, the soil, the sunlight. A reminder that even the invisible has weight in the story of life. What if the rhythm of ice ages, rising and falling like the breath of the planet, was not only a product of Earth's cycles but also nudged by forces beyond our world? To imagine this, we must stretch our perspective to spans of tens and hundreds of thousands of years, where glaciers grow and retreat, where oceans shift, and where whole landscapes change. Human ancestors lived within these rhythms, adapting not to a single climate but to a moving balance, sometimes warm, sometimes cold. Their story is interwoven with these long environmental pulses. Now we pause with the mechanism. Ice ages are influenced by many factors: Earth's orbital cycles, shifts in tilt, the slow wobble of the axis. Yet these patterns alone do not explain every turn. Variations in solar activity, or encounters with interstellar clouds, may have added subtle layers. When the sun is less active, its shielding weakens, allowing more cosmic rays to reach the atmosphere. Some researchers suggest this may increase cloud cover, cooling the planet. Dust from beyond the solar system, drifting into Earth's skies, could also reduce sunlight, tipping the balance toward colder climates. These influences are not constant, but when added to Earth's own cycles, they may have amplified the onset of glaciations. The evidence for such ideas is indirect. Ice cores from Greenland and Antarctica reveal patterns in oxygen isotopes, reflecting temperatures of the past. In these frozen records, we see the repeated rise and fall of ice ages, aligned with orbital cycles, yet with variations that remain unexplained. In ocean sediments, tiny fossils show shifts in chemistry, marking cold seas and warm seas, ice advances and retreats. Occasionally, isotope markers such as beryllium-10 suggest higher cosmic ray activity, hinting at times when solar or galactic influences reached Earth more strongly. These are the quiet traces, not proof of cause, but reminders of connection. Now let us linger with a thought experiment. Imagine Earth passing through a denser region of interstellar dust. For thousands of years, sunlight dims slightly. Summers are cooler, glaciers expand. Human ancestors, already living on shifting savannas, find their ranges changing. Some follow animals into new valleys, others move southward, seeking more stable climates. In these migrations, populations separate, adapt to different conditions, and slowly diverge. Genetic variation increases, not because the dust acts directly, but because climate pressures reshape survival. Or imagine another scenario: the sun enters a long quiet phase. Cosmic rays rise, cloud cover thickens, cooling Earth. Lakes shrink, grasslands widen. Early humans face scarcity of food and water, forcing cooperation, innovation, perhaps the first steps towards symbolic thought, as groups rely on shared memory and planning. In both cases, the changes are gradual, almost invisible within a lifetime, yet across millennia they shape the stage of evolution. We must remain cautious. The link between cosmic influences and ice ages is still debated. Climate is a complex system, influenced by volcanoes, tectonics, and ocean currents as much as by the sky. Absence of clarity does not mean absence of influence, but it does remind us to hold the idea gently, without overstating its weight. What we can say is that the timing of human evolution coincided with a world of changing climates, and these climates were not shaped by Earth alone. Now we soften into perspective. The great glaciers, advancing and retreating, were part of the environment that formed us. Whether nudged by cosmic dust, by solar quiet, or only by Earth's own rhythms, they created conditions that required resilience and movement. Human ancestors did not evolve in stability but in flux, learning to survive in landscapes that never stayed the same. To recognize this is to see ourselves as children not only of Earth but of a wider interplay, where even distant events leave faint marks. We let this thought rest, like snows settling on stone, silent yet shaping the ground beneath. What if the path of our evolution was gently guided not only by Earth's landscapes but also by the larger movements of our solar system as it drifted through the galaxy? To picture this, we need to expand our sense of place. Our planet does not sit still. It circles the sun, and the sun itself orbits the center of the Milky Way. This journey takes hundreds of millions of years, carrying Earth through regions of space that are sometimes quiet, sometimes crowded with gas and dust, sometimes brushed by the effects of nearby stars. Over such timescales, these encounters may have influenced the climate and environments that shaped human ancestors. The mechanism is simple in principle but slow in effect. When the solar system passes through denser clouds of interstellar dust, more particles enter Earth's atmosphere. This may dim sunlight slightly, cooling the climate, or alter chemistry in the upper air. When we move through quieter regions, conditions ease. The solar system's path also brings us nearer or farther from clusters of stars. A nearby supernova, occurring within a few dozen light-years, can send a wave of cosmic rays that reaches Earth, raising radiation levels for centuries. These changes, while not sudden disasters, may add pressure to the cycles of ice ages, to the availability of habitats, to the survival of species. The evidence is faint but present. Layers of ocean sediments contain isotopes, such as iron-60, that can only come from supernovae. Their presence marks times when Earth was touched by stellar debris. Ice cores and geological records show periodic variations in climate that may align not only with Earth's orbit but also with the solar system's galactic journey. These are indirect signals, subtle and often debated, but they remind us that our planet does not travel alone. It moves through a changing environment of stars and dust. Now let us linger with a thought experiment. Imagine the solar system entering a dense interstellar cloud. For tens of thousands of years, the sky is filled with more dust. Sunlight reaching Earth is reduced, not enough to plunge into darkness, but enough to tip the balance of climate toward cooling. Glaciers advance. Grasslands expand. Human ancestors living in Africa find forests shrinking, forcing them into more open landscapes. Upright walking becomes more useful. Tool use grows as survival demands new strategies. The cause is distant, yet the effects ripple into evolution. Or imagine the opposite. Earth passes through a clearer region of the galaxy, sunlight strong, climates warmer. Forests spread, animals migrate differently. Human groups adapt again, finding new foods, exploring new territories. In both cases, cosmic geography sets the stage, while evolution plays out upon it. We must hold these possibilities with care. The scales of time are vast, and many other factors, volcanoes, orbital shifts, impacts, intertwine with galactic influences. It is impossible to draw a straight line from a region of dust in the galaxy to a specific human trait. Absence of proof does not equal absence of effect, but neither should we overstate what we cannot confirm. What we can say is that Earth is not isolated. Its long orbit through the galaxy places it in changing conditions, and those conditions have likely touched the climate and environments in which humans arose. Now we soften into perspective. When we look at the night sky, we see stars spread across darkness, but we are also looking into the environment through which our planet moves. The galaxy is not a backdrop, it is part of the context of life. Our ancestors adapted within rhythms set not only by Earth and Sun but also by the slow journey of the solar system. To recognize this is to see our story as part of a larger movement, woven into the currents of the Milky Way. We let this thought rest, quiet as starlight, reminding us that even the most distant scales can touch the most intimate parts of our history. What if the faint rhythm of solar cycles, the quiet waxing and waning of the sun's activity, had a hand in shaping the path of human evolution? To imagine this, we need to see the sun not as a constant lamp but as a living star, with moods and patterns that unfold over years, centuries, and even millennia. Every 11 years or so, the sun's magnetic field flips, and with it, the number of sunspots rises and falls. During active periods, solar storms send bursts of charged particles into space. During quieter phases, the sun's protective shield weakens, allowing more cosmic rays to reach Earth. These cycles are small on human scales, yet over long stretches they may leave traces that matter. Now we pause with the mechanism. When the sun is active, its strong solar wind pushes cosmic rays away, reducing the radiation that enters Earth's atmosphere. When the sun is calm, cosmic rays flow more freely, creating isotopes such as carbon-14 and beryllium-10. These isotopes are stored in tree rings and ice cores, leaving a record of solar rhythms that we can still read today. Beyond isotopes, solar cycles may influence climate. A slightly weaker sun does not reduce light dramatically, but the changes can interact with Earth's systems, altering wind patterns, rainfall, or ocean circulation. Over decades, these shifts can reshape environments. For early humans, even small changes in rainfall or vegetation could determine where water was found, where herds migrated, and where survival was possible. The evidence remains indirect. Ice cores show clear records of isotope variations linked to solar cycles. Tree rings, too, reveal rhythms of growth tied to changing radiation. Historical records, though much younger, describe periods of colder winters and failed harvests during prolonged solar minima, such as the so-called Little Ice Age. These are echoes of how solar variability can ripple through climate and life. Yet the further back we look, the harder it is to link these cycles to specific evolutionary changes. Absence of direct proof does not mean absence of influence, but it does remind us to tread carefully. Now let us linger with a thought experiment. Imagine a long solar minimum lasting centuries. Cosmic rays increase, cloud cover thickens, and Earth cools slightly. For human ancestors living on the edge of survival, colder seasons may push groups to move southward, or to invent new ways of storing food, or to rely more on cooperation. Small changes in climate, stretched over generations, create pressures that shape behavior and adaptation. Or imagine instead a prolonged period of high solar activity. The stronger solar wind shields Earth more fully, reducing cosmic rays, changing patterns of atmospheric chemistry. Rainfall shifts, rivers swell or shrink. Populations adjust, some flourishing, others declining. Over long times, these repeated nudges may accumulate, weaving solar rhythms into the background of human history. Now we rest with perspective. The sun is our nearest star, and its rhythms are part of the environment in which all life has unfolded. For us, its influence is most often felt as warmth and light, but in quieter ways, its cycles may also have touched the climates, the migrations, and the challenges that shaped our ancestors. We cannot know exactly how strong this influence was. Perhaps it was minor, perhaps greater. What we do know is that the traces of solar cycles are written into archives of ice and wood, into the memory of landscapes themselves. They show us that even the familiar sun carries patterns that ripple outward into life. We let this thought rest gently, like sunlight filtered through leaves, steady but always moving, part of the quiet background of our story. What if the slow breathing of the atmosphere, its quiet shifts in composition over deep time, was partly touched by forces arriving from space, leaving conditions that influenced the course of our evolution? To think of this, we must picture the air not as an unchanging blanket but as a living archive. Within it are gases that sustain life, oxygen, carbon dioxide, nitrogen, and within their proportions lies the delicate balance of climate, of breathing, of survival itself. Most of these changes arise from Earth's own cycles. Volcanoes release gases, plants absorb and exchange, oceans act as vast reservoirs. Yet from time to time, the balance may have been altered by what arrived from beyond. Dust from comets, fine grains drifting through the solar system, can enter the atmosphere and linger. These particles are too small to see, yet when enough accumulate, they can scatter sunlight, cooling the surface. Meteorite impacts, larger and rarer, release dust and gases on a different scale, sending particles into the stratosphere where they remain for years. Radiation from the sun or from distant stars can also change the chemistry of the air, splitting molecules apart and letting them recombine in new ways. Each of these influences, faint or dramatic, leaves traces, not always clear but sometimes measurable. The evidence for such cosmic fingerprints lies in indirect records. In ice cores, bubbles of ancient air are trapped, preserving the exact mixture of gases from thousands of years ago. Some layers show unusual spikes, tiny moments of higher dust, altered chemistry, or rare isotopes that suggest influences beyond Earth. In sediments, too, we find changes that cannot be explained solely by volcanic or biological processes. The presence of isotopes such as beryllium-10, produced when cosmic rays interact with the atmosphere, points to times when radiation was stronger, leaving a marker like an ink blot in the long diary of the air. Now let us pause with a thought experiment. Imagine a period when Earth passes through a denser interstellar cloud. The sky grows slightly dimmer, not enough to be dramatic but enough to cool climates. Glaciers expand, rainfall patterns shift. For human ancestors, the difference means rivers run in new courses, grasslands appear where forests stood, and animals migrate differently. Populations must adapt, moving with the water, changing diets, inventing new ways of living. The cosmic cloud is distant, yet its presence reshapes daily survival. Or imagine a series of comet dust showers, arriving over centuries. The fine particles settle into the atmosphere, altering sunlight and perhaps even chemistry. The cooling is modest but lasting. Human groups face leaner harvests, scarcer game. Social bonds tighten as cooperation becomes more necessary. Those who share resources endure, those who isolate struggle. In this way, the air itself, touched by cosmic dust, shapes not just biology but behavior. We must remain cautious. Many of these influences are hypotheses, difficult to separate from Earth's own powerful systems. Volcanoes, oceans, forests, these dominate the chemistry of the air. Cosmic contributions are likely small, subtle, and rare. Yet absence of certainty does not mean absence of effect. Even faint influences, spread across thousands of years, may ripple into the story of evolution, not as commands but as nudges. Now we soften into perspective. The atmosphere has always been a meeting place, where earth and sky interact. It is our shield, our breath, our climate. Within it are the traces of countless exchanges, gases released from stone, from ocean, from life, and perhaps, at times, from beyond our world. Human evolution unfolded within this shifting balance, shaped by air that was never exactly the same. To remember this is to see ourselves not apart from the cosmos, but as beings who live within its subtle touch. We let this thought rest quietly, like a breath itself, steady, unnoticed, but carrying with it the memory of the wider universe. What if the quiet pull of other planets, moving with us around the sun, subtly influenced the conditions in which humans evolved? To imagine this, we need to think of the solar system not as a set of isolated worlds, but as a web of gravitational threads. Each planet, large or small, contributes to the balance. Jupiter, the giant among them, exerts the greatest influence. Its mass bends the paths of comets and asteroids, often diverting them away from Earth, sometimes sending them inward. Saturn, too, adds its pull, shaping the rhythm of orbits. These forces do not act on us directly, but they help set the stage on which life unfolded. Now we pause with the mechanism. Gravitational influence is subtle yet persistent. Over long periods, the tugs of other planets shift Earth's orbit slightly, adjusting its eccentricity, how stretched the path around the Sun becomes. These shifts contribute to the cycles that drive ice ages and warm periods. Jupiter's role as a shield is also often discussed. Its gravity sweeps up comets and asteroids, reducing the number that reach Earth. Yet it is not only protective. Sometimes Jupiter's pull sends objects into the inner solar system, increasing the chance of impacts. These impacts, rare but powerful, can alter climates and ecosystems. In this way, the planets, without intention, become part of the chain of influences that shape the environment in which humans emerged. The evidence is indirect but recognizable. Models of orbital mechanics show how planetary alignments affect Earth's long-term cycles. Geological layers contain markers of impacts, some of which may have been steered by giant planets. The rhythm of ice ages aligns with orbital variations that arise from these gravitational dances. Though we cannot point to a single human trait and trace it to Jupiter or Saturn, we can see the background of climate and habitability shaped in part by their presence. Now let us linger with a thought experiment. Imagine a solar system without Jupiter. The belt of asteroids between Mars and Jupiter might have remained less stable, sending many more bodies toward Earth. Impacts would be more frequent, perhaps too frequent for complex life to flourish steadily. Human evolution in such a world might have been disrupted repeatedly, progress slowed, or paths diverted. Or imagine another scenario, Jupiter slightly closer, exerting stronger pulls. Orbital cycles of Earth could become more extreme, climates more volatile. Human ancestors would face harsher transitions, perhaps developing even greater adaptability, or perhaps struggling against instability. In both cases, we sense how the arrangement of planets could shape the conditions for life without directly touching it. Now we turn to limits. These ideas remain cautious, framed by models and probabilities. The actual history of impacts and climate change is complex, with many causes interwoven. To say that planets determined our path would be too strong. To say they played no role at all would ignore the evidence of orbital cycles and cosmic shielding. The truth lies somewhere between, an influence that is real, but layered among many others. Now we soften into perspective. When we look at the night sky and see bright points like Jupiter, Saturn, or Venus, we are not only seeing distant worlds. We are seeing neighbors that have long been part of the balance of our existence. Their gravity has shaped orbits, deflected rocks, and tuned cycles of climate. Human evolution unfolded within this balance, carried along quietly by the unseen pull of planetary companions. We let this thought rest, gentle as a tide shaped by distant moons, reminding us that even worlds we never touched have shaped the one we call home. What if the moon, our closest celestial companion, played a quiet yet decisive role in the unfolding of human evolution? To consider this, we must first see the moon not as a passive ornament of the night sky, but as an active participant in shaping Earth's rhythms. Its gravity draws at the oceans, raising tides, moving water back and forth like the slow breathing of the planet. These tides, over millions of years, have sculpted coastlines, nourished estuaries, and created environments rich in resources. For our ancestors, who often lived near water, these tidal zones may have been vital sources of food and safety. The moon also stabilizes Earth's tilt. Without it, the axis might wander chaotically, leading to extreme swings of climate. With it, the tilt remains relatively steady, keeping seasons within bounds that life can adapt to. In this way, the moon has long been a quiet anchor of habitability. Now let us pause with the mechanisms. Tides are a result of the moon's pull on Earth's oceans. Twice each day, waters rise and fall, exposing and covering shorelines. For early humans, such areas offered shellfish, stranded fish, and seaweed, nutrient-rich foods that may have supported brain growth. The rhythm of tides also created predictable patterns, fostering awareness of cycles and time. In addition, the moon's brightness at night extended visibility. Even before fire, moonlight gave opportunities for movement, for hunting, for gathering, shaping behavior and habits. These influences are subtle, but their persistence may have nudged our path. The evidence is not direct but can be sensed in traces. Archaeological sites near ancient coasts reveal reliance on tidal foods. Shell middens, layers of discarded shells, stand as archives of human diets reaching far back. Some scholars suggest that the rich nutrients from marine sources, particularly fatty acids essential for brain development, were important in shaping human cognition. In this way, the moon's pull, by shaping tides, may have indirectly supported the growth of minds capable of imagination and culture. Now let us linger with a thought experiment. Imagine Earth without a large moon. The tilt of the axis drifts unpredictably. Sometimes winters are harsh, summers intense. Climates swing, making survival unstable. Populations struggle to adapt to environments that change too quickly. Perhaps complexity of life arises more slowly, or not at all. Or imagine instead that the moon is present, but smaller. Tides are weaker, coastlines less dynamic. Fewer tidal pools form, fewer rich food sources are available. Human ancestors may rely more heavily on terrestrial diets, delaying or altering the trajectory of brain development. In both cases, the absence of the moon's steadying hand shifts the conditions of life in ways that ripple into evolution. We must be cautious here. The exact role of the moon in human evolution cannot be pinned down. Many other forces shaped our history: climate, geology, chance. Yet the moon's influence on tides, stability, and night light is undeniable, and its contribution may have been more than background. Even if it was only one of many threads, it was a thread woven into the fabric of our story. Now we soften into perspective. The moon has always been with us, a constant presence in the night sky, cycling through its phases with patience. It shaped waters, stabilized seasons, and lit the darkness. Human evolution unfolded under its watch, in ways we may never fully measure but can quietly sense. To look at the moon is to look at a companion that has been with us since the beginning, a reminder that our story is tied not only to Earth but also to the rhythms of the sky. We let this thought rest here, calm and enduring, like the light of the moon reflected gently on still water. What if the cycles of fire from within Earth, volcanic eruptions, were not only local events but also tuned at times by cosmic influences, leaving imprints on the environments in which human ancestors evolved? To picture this, we must widen our view. Volcanoes are born from Earth's inner heat, yet their timing and intensity may be nudged by stresses that come from beyond. Large impacts can crack the crust, setting magma free. Gravitational pulls from the moon and planets may subtly adjust stresses underground. Even the loading and unloading of ice sheets, themselves influenced by orbital and perhaps galactic cycles, can awaken volcanoes long dormant. In this way, forces of earth and sky may have met in fire. Now let us pause with the mechanism. Volcanic eruptions release ash, gases, and molten rock. Locally, they can devastate. Globally, when eruptions are large, they send fine ash and sulfur into the stratosphere, where particles linger, scattering sunlight. The world cools for years, sometimes for decades. For human ancestors, such cooling meant shorter growing seasons, less food, harder survival. Volcanic winters, though temporary, could pressure small populations, shaping the paths of adaptation, migration, and resilience. The evidence rests in layers. In ice cores, thin dark bands preserve volcanic ash, matched with chemical signatures of sulfur. In sediments, too, we find traces of ancient eruptions. Some of these align with key moments of human prehistory. The Great Eruption of Toba, about 74,000 years ago, left signals across the globe. Its ash fell in India, its gases cooled the planet. Some studies suggest human populations shrank in its wake. Others argue the effect was less severe. What remains certain is that such events mark turning points in the environment. Now let us linger with a thought experiment. Imagine a massive eruption coinciding with a time of cosmic dust passing through the solar system. Cooling from the eruption adds to the dimming already present. For human groups, this means years of scarcity. Many perish, but some find ways to endure, turning to cooperation, sharing food, migrating toward less affected regions. Their survival shapes the future gene pool, not by design but by persistence. Or imagine another path. Cosmic rays, increase during a quiet sun, alter weather patterns, shifting rainfall. Volcanoes, already restless, erupt more frequently as ice sheets thin and release pressure. Human ancestors, living near fertile volcanic soils, benefit from rich harvests in good years but must flee in times of fire. The rhythm of challenge and opportunity forges adaptability, a trait that becomes central to survival. We must hold these ideas with care. Volcanoes arise primarily from Earth's own dynamics, from deep heat and shifting plates. Cosmic and orbital influences, if present, are secondary nudges, not causes. The traces we find, ash in ice, isotopes in sediments, tell us of eruptions, but not always of their triggers. Absence of proof does not mean absence of connection, but we cannot overstate what remains uncertain. Now we soften into perspective. Volcanoes are reminders of Earth's restlessness, of its inner fire always seeking release. For humans, they were both destroyers and givers, taking lives yet leaving behind fertile soils where communities thrived. Whether their rhythms were tuned in part by cosmic forces or only by Earth itself, they formed part of the stage on which our story unfolded. To recognize this is to see our evolution as shaped not just by steady climates but by sudden turns, by challenges that demanded resilience. We let this thought rest quietly, like cooled lava on a hillside still holding the memory of fire and the hint of forces that reach far beyond. What if Earth's magnetic field, that invisible shield wrapping around us, was more than protection against radiation, but also a quiet force shaping the course of human evolution? To imagine this, we must step back and see the magnetic field as both a guardian and a storyteller. Generated deep in Earth's molten core, It extends far into space, deflecting charged particles from the sun and beyond. Without it, the surface of Earth would be bombarded more directly, atmospheres might erode faster, and radiation would reach living cells more strongly. With it, life unfolds under a gentler sky. Yet the field is not fixed. It shifts, wobbles, and sometimes flips entirely. These reversals, when north becomes south and south becomes north, leave their signature in rocks, frozen like pages of a vast archive. For us, the significance may have been subtle but real. Now let us pause with the mechanism. The field is created by the motion of liquid iron in Earth's outer core, much like electricity flowing through wires creates a magnetic field. This geodynamo has been active for billions of years. The field does not block radiation entirely, but it reduces the flow of cosmic rays reaching the surface. When it weakens, more radiation arrives. This radiation can alter DNA, increase mutation rates, and influence climate by affecting the chemistry of the atmosphere. Over millions of years, such variations may have contributed to evolutionary pressures. The evidence lies in indirect traces. Rocks record the orientation of the magnetic field at the time they formed, showing us a history of flips and fluctuations. Sediments and ice cores, too, hold isotopes like beryllium-10 and carbon-14, produced when cosmic rays strike the atmosphere. Periods of high production suggest weaker magnetic fields, when Earth's shield was less effective. In these times, life may have experienced slightly higher doses of radiation. Though we cannot point to exact genetic changes caused this way, the rhythms of reversals and variations remain part of the background in which evolution occurred. Now let us linger with a thought experiment. Imagine a period when Earth's magnetic field weakens for thousands of years, as often happens before a reversal. Cosmic rays increase. For human ancestors, the difference is not dramatic in a single lifetime, but across many generations it leaves its mark. Mutations appear more often. Some are harmful, many neutral, a few beneficial. Traits emerge, perhaps stronger immune responses, or small shifts in physiology that help survival. Over time, these become part of the human line. Or picture another scenario, a full reversal, when the field collapses to a fraction of its strength before rebuilding. During this time, the skies glow with stronger auroras, radiation rises, and climates shift slightly as atmospheric chemistry changes. Populations may respond by moving, by clustering in safer areas, by adapting socially and biologically to new stresses. The magnetic field, unseen, would have been part of the quiet conditions shaping choice and chance. We must remain cautious. The timing of reversals and their effects on life are still debated. Some reversals align with extinctions or climate shifts, others do not. The field is only one piece in a complex web. Absence of clear evidence does not mean absence of influence, but it reminds us to avoid certainty where none exists. Now we soften into perspective. The magnetic field has been with Earth as long as complex life, shielding and fluctuating, recording its history in stone. For humans, it has always been there, unseen yet protective, shaping the environment in which we evolved. Its variations may have added subtle pressures, nudging the flow of mutations, altering climates, influencing migrations. To stand under the aurora today is to glimpse this hidden companion, to see light shaped by invisible lines that circle the planet. We let this thought rest gently, like a compass needle settling into place, quiet, steady, guiding without noise yet always present. What if the great extinctions of the past, those quiet turning points in life's history, were not only shaped by Earth itself but also nudged by influences beyond our planet? To imagine this, we must stretch our sense of time into hundreds of millions of years, when life rose, flourished, and sometimes was cut back suddenly. Extinction is not an end but part of the rhythm of evolution, clearing space for new forms to arise. For humans, our story begins long after many such events, yet the conditions that allowed us to appear were set by these earlier upheavals. Now let us pause with the mechanisms. Extinctions can be caused by many things: volcanic outpourings, shifting continents, climate change. But often, the triggers seem to align with events beyond Earth. A massive asteroid strike 66 million years ago left a layer rich in iridium, an element rare on Earth but common in meteorites. This mark in the rocks tells us of the impact that ended the age of dinosaurs, clearing ecological space in which mammals, and eventually humans, could rise. Other extinctions may link to supernovae, cosmic explosions that bathe Earth in radiation. Such events might thin the ozone layer, letting more ultraviolet light reach the surface, stressing ecosystems already vulnerable. The evidence is subtle, written in isotopes and sediments, and in the sudden changes in fossil records. These are not direct records of cause but quiet reminders of connections stretching beyond our planet. Now we can linger with a thought experiment. Imagine a human world never touched by the asteroid at the end of the Cretaceous. Dinosaurs remain the dominant land animals. Mammals, small and hidden, continue in the shadows. Without that extinction, the path to primates and to us might never open. Or picture another scenario: a supernova closer than most, its radiation raising mutation rates in plants and animals. Some species decline, others adapt. Over millions of years, these shifts ripple outward, creating the branches of evolution we later inherit. Human ancestors may carry in their lineage traits shaped by those distant bursts of starlight. We must remain cautious. The link between cosmic events and extinctions is not always clear. Some extinctions align neatly with impacts or isotope spikes, others do not. Many may be the result of multiple factors, Earth's restlessness mixed with influences from the sky. Absence of simple answers is itself a reminder of complexity, and of the need for humility when reading the record of life. Now we soften into perspective. Extinctions, though often seen as endings, are also beginnings. They create the spaces in which new forms can grow. For humans, our very existence may be traced to such clearings. Without them, the path might have been different, or not open at all. Whether triggered by Earth, by the cosmos, or by both, they remind us that evolution is not steady progress but a sequence of rises and falls, woven into the larger fabric of time. We let this thought rest quietly, like a shadow laid across stone, reminding us that even endings are part of the long story of life, and that our own emergence was shaped as much by what vanished as by what endured. What if cosmic radiation, that steady drizzle of high-energy particles from distant stars and galaxies, played a quiet role in shaping the path of human evolution? To imagine this, we must think of space not as empty but as filled with invisible messengers. These particles, called cosmic rays, travel vast distances before reaching Earth. Most are blocked by our atmosphere and magnetic field, yet some slip through, interacting with our cells, leaving tiny marks in DNA. These marks are usually neutral or harmful, but every so often a change offers an advantage. Over millions of years, such small differences accumulate, part of the silent background of evolution. Now let us pause with the mechanism. Cosmic rays are mostly protons moving at nearly the speed of light. When they strike the upper atmosphere, they create showers of secondary particles, which in turn generate isotopes such as carbon-14 or beryllium-10. These isotopes become part of ice, sediments, and even living organisms, forming a quiet record of radiation through time. At ground level, radiation from cosmic rays is faint compared to natural radioactivity from rocks, yet it is steady. In higher places, like mountains or high plateaus, the dose is stronger. For our ancestors, who sometimes lived in such regions, this difference may have mattered. More mutations could mean more genetic variety, and variation is the raw material of evolution. The evidence is indirect but persistent. Ice cores from Antarctica and Greenland show patterns of beryllium-10 that align with times of high cosmic activity, often linked to quiet phases of the Sun when its shield weakens. Tree rings, too, carry the traces of carbon-14, another isotope born from cosmic rays. In fossils and ancient DNA, we cannot trace single mutations back to cosmic rays, but we can see that mutation is constant, and cosmic radiation is one of its quiet contributors. It is a background whisper, rarely noticed, but always present. Now let us linger with a thought experiment. Imagine a long period when the Sun is unusually calm. Cosmic rays flow more freely into Earth's atmosphere. The climate cools slightly from the added cloudiness, But at the same time, mutation rates rise. Over many generations, some lineages gain traits that prove useful, perhaps better adaptation to cold or resistance to disease. These traits spread slowly, not because of intention but because of survival. Or picture another path. A nearby star ends its life as a supernova, showering Earth with an increased flux of cosmic rays for centuries. Radiation levels rise. Some species struggle, some vanish, others adapt. Human ancestors, small and scattered, endure by resilience, carrying forward genetic changes that will later shape us. The link is not direct but woven into probabilities, nudges rather than commands. We must be cautious here. Most mutations are random, and many arise from processes within cells themselves. Cosmic rays are only one source among many. To say they shaped evolution directly would be too strong. Yet to ignore them would miss a part of the wider environment in which life has always unfolded. The absence of clear proof does not mean absence of influence. It means only that the traces are subtle, hard to disentangle from the noise of time. Now we soften into perspective. Cosmic radiation is part of the universe itself, a reminder that even distant stars leave their touch upon us. For humans, it was never a dramatic force, but perhaps a quiet sculptor, adding variation, shaping possibilities. We evolved not in isolation but in constant exchange with the cosmos, even at levels too small to see. To recognize this is to feel a wider connection, that our story is not only of Earth and its climates but of particles traveling across light years to meet us. We let this thought rest gently, like a faint trace on film exposed to starlight, subtle, almost invisible, but undeniably part of the picture. What if the slow drift of Earth through the galaxy, its quiet journey among stars and clouds of matter, had its own influence on the story of human evolution? To imagine this, we must picture our solar system not as fixed in place, but as a traveler. The Sun, with all its planets, moves through the Milky Way at great speed, circling the galactic center once every 225 million years. In that time, we pass through different regions, spiral arms rich in stars, quieter interarm spaces, clouds of gas and dust. Each passage may bring subtle changes to the environment of Earth, not immediately visible, but unfolding over long spans of time. Now let us pause with the mechanisms. Galactic movement may influence us through radiation, dust, and gravity. When we pass through denser regions, cosmic rays can increase, altering atmospheric chemistry and raising mutation rates. Dust clouds can dim the sunlight slightly, cooling the climate. Encounters with molecular clouds, vast, cold accumulations of gas, might even disturb the Oort cloud, the distant shell of comets around the solar system, sending some inward toward Earth. In this way, the galaxy itself becomes part of the conditions in which life evolves. The evidence, though faint, can be read in traces. Geological layers show periods of unusual isotope concentrations, such as iron-60, thought to be deposited by nearby supernovae. Sediment records suggest times of cooling and ice advance that may align with passages through spiral arms. These are not precise matches, but patterns that hint at connections. The language of traces is quiet but enduring: isotopes, sediments, fossil shifts, all offering indirect clues to galactic rhythms. Now let us linger with a thought experiment. Imagine Earth passing through a spiral arm rich in massive stars. Some of those stars end their lives in supernovae, sending radiation and cosmic rays across space. The atmosphere responds with chemical changes, the climate cools, mutation rates rise. Over thousands of years, ecosystems adapt. For human ancestors, such changes mean new landscapes to navigate, new pressures to face. Some groups move, some vanish, some endure. The galactic passage becomes part of the background of survival. Or picture another path: the solar system enters a thick molecular cloud. Dust spreads in the upper atmosphere, dimming sunlight. Crops and plants struggle, ecosystems shift. Human populations respond with ingenuity, finding new food sources, storing what can be stored, moving to safer regions. The pressure of scarcity fosters cooperation, shaping cultural as well as biological evolution. Again, the galaxy's quiet drift leaves an imprint, not as a sudden shock but as a gradual influence. We must remain cautious. The timing of galactic passages and their effects on Earth are uncertain, mapped with models that still carry gaps. Correlations with climate or extinction events are intriguing but not definitive. Absence of certainty does not erase possibility, but it reminds us to read the record gently, without forcing conclusions. Now we soften into perspective. The Milky Way is vast, and our solar system's orbit within it is a journey so slow we cannot feel it. Yet across millions of years, this motion may have been part of the shaping environment of life. Human evolution unfolded within this wider context, under influences both local and cosmic. To remember this is to see ourselves as passengers not just on Earth, but within a galaxy whose rhythms stretch far beyond our perception. We let this thought rest quietly, like the faint glow of the Milky Way overhead, constant yet moving, a reminder of the larger voyage we share. What if the faint but steady background of the universe itself, the cosmic microwave radiation left from the birth of everything, quietly touched the path of life and the evolution of humans? To sense this, we need to imagine space not as silent emptiness, but as filled with a very old whisper. This radiation is the afterglow of the Big Bang, spread evenly across the sky. It is extremely weak, almost imperceptible, yet always present. It washes through us, through our planet, through every living thing. Though it does not strike with force, it forms part of the subtle environment in which life arose and changed. Now let us pause with the mechanism. The cosmic microwave background, or CMB, is a form of light, stretched into microwaves by billions of years of expansion. Unlike sunlight, it does not warm us directly, yet it adds the faintest layer to the background of radiation on Earth. This radiation is steady, uniform, with small ripples that map the early structure of the universe. For life, the CMB is more context than cause, but still, some scientists wonder whether its gentle pressure, its steady hum, contributed to processes in ways we cannot easily trace. Radiation, after all, can influence matter on the smallest scales. Though weak, it is persistent, and persistence, over deep time, sometimes leaves traces. The evidence is not found in fossils or bones, but in the sky itself. Instruments have mapped the CMB in exquisite detail, showing patterns of tiny fluctuations, temperature differences of less than 1/1000th of a degree. These patterns shaped how galaxies and stars formed. And without galaxies, without stars, there would be no Earth, no Sun, no evolution. In this sense, the CMB is not just background noise, it is the first framework of the cosmic stage. We see its imprint in the structure of the universe, in the distribution of galaxies, and indirectly, in our own existence. Now let us linger with a thought experiment. Imagine that the CMB had been slightly stronger, just a little more energetic. The early universe might have evolved differently. Stars could have formed sooner, galaxies clustered more tightly, supernovae exploding in greater numbers. Earth might have arisen in a different neighborhood, under a harsher sky, with life facing more radiation and more instability. Perhaps evolution would have taken a slower, more uncertain path. Or imagine the opposite, a weaker CMB, leaving matter more scattered. Galaxies would form later, stars more sparsely. Perhaps Earth would not yet exist, or life would still be in simpler forms. In both scenarios, the faint background of microwaves, though barely noticeable, plays a role in setting the stage. We must be cautious here. For human evolution directly, the CMB likely had little direct influence. Its effect is more ancient, more foundational, shaping the structure in which stars, planets, and life could later appear. To say it shaped human traits would be too strong. But to say it is irrelevant would miss its deep role as the quiet background upon which all else rests. Now we soften into perspective. The CMB is the oldest light we can see, a relic from when the universe was young. It does not guide us day to day, but it reminds us that our story is woven into a larger one, stretching back almost to the beginning of time. Humans evolved under skies filled not only with stars but with this unseen glow, a reminder that we are part of a universe that still carries its memory of birth. We let this thought rest gently, like a hum in the background of silence, always there, always surrounding us, quiet as breath, endless as the sky. What if the very constants of physics, those delicate balances that define the structure of the universe, were slightly different, and through that difference the path of human evolution unfolded in another way? To think of this, we must imagine not sudden events but quiet conditions, numbers and ratios that seem abstract yet determine how stars burn, how atoms hold together, how life can arise at all. Constants such as the strength of gravity, the charge of the electron, or the speed of light may feel distant from our daily lives, yet they form the invisible framework within which every step of evolution has taken place. Now let us pause with the mechanisms. The constants of physics are values that do not change with time or place. They set the rules of interaction. If gravity were stronger, stars would burn faster, perhaps too quickly for planets like Earth to form stable conditions. If it were weaker, stars might never ignite, leaving a cold, dark universe. If the strength of the electromagnetic force shifted, atoms might not bond into molecules, or chemical reactions might run too sluggishly for life to emerge. Within the narrow window we inhabit, complex chemistry is possible. Stars live long enough for planets to stabilize, and DNA can form and replicate. The evidence for these constants is all around us. Astronomical observations show that stars behave according to the same physics across billions of light years. Laboratory experiments confirm the same values to many decimal places. Geological records on Earth show continuity, the chemistry of rocks, the decay of isotopes, all consistent across immense spans of time. These are indirect signs that the constants have remained steady, at least to the precision we can measure. Yet in the quiet gaps of knowledge, some wonder if tiny variations could have occurred, nudging processes in ways we do not yet see. Now let us linger with a thought experiment. Imagine that the fine structure constant, which governs how strongly electrons cling to nuclei, were just a little higher. Chemistry would be different. DNA might not fold in the same way. Life, if it arose at all, might favor other patterns, slower or faster, perhaps leading to beings unlike us. Or imagine that gravity's pull were slightly stronger. Stars would live shorter lives, supernovae more frequent. Earth might have formed under skies more turbulent, with evolution pressed by harsher radiation and faster changing climates. Human ancestors, if they appeared, might carry traits of resilience to instability, shaped by a world less stable than the one we know. We must remain cautious here. No evidence tells us that these constants have shifted within the span of life on Earth. Their values appear steady, universal, unchanging. To link them directly to human evolution is speculative. Yet their very steadiness may itself be the influence, providing the stable stage upon which evolution could unfold. Without that stability, our path might not have been possible at all. Now we soften into perspective. The constants of physics are the quietest of conditions, unchanging yet profoundly influential. They form the deep framework of possibility, setting boundaries within which stars, planets, and life can exist. For humans, their role is invisible but absolute, the unseen foundation beneath every adaptation, every migration, every thought. To reflect on this is to recognize that our story is not only of Earth or cosmos but of the laws that hold them both. We let this thought settle gently, like the steady tick of a clock that never falters, marking time without noise, shaping the rhythm of all that lives. What if, after all the forces we have considered, the stars, the impacts, the quiet rain of radiation, the slow drift through the galaxy, the greatest influence on human evolution from beyond Earth was not any single event, but the long awareness of our place in the cosmos itself? To imagine this, we must shift from physical forces to the subtler realm of perception. For countless generations, humans have lifted their eyes to the night sky. The stars, the phases of the moon, the wandering planets, all these patterns shape not our genes directly, but our minds, our cultures, and the ways we learn to adapt. Evolution is not only about bodies, it is also about thoughts, cooperation, and imagination. Now let us pause with the mechanisms. When early humans gathered around fires, the sky above them was their constant map. The stars marked seasons, migrations of animals, the right times to plant and harvest. This knowledge increased survival. Those who learned the language of the heavens passed it on, and with it came myths, calendars, and shared meaning. Over time, the habit of looking outward may have shaped our brains as much as our tools did, giving us a sense of time, of cycles, and of belonging to something larger. The evidence of this is indirect yet plentiful. Ancient stone circles, aligned with solstices and equinoxes. Caves painted not only with animals but with dots that may echo constellations. Clay tablets carrying records of eclipses. Oral traditions that mirror celestial events. These are not genetic fossils, but cultural ones, traces of how the cosmos imprinted itself upon us. The language of traces here is written not in isotopes or sediments, but in memory, ritual, and the architecture of ancient places. Now let us linger with a thought experiment. Imagine human ancestors without the stars, perhaps living under a permanent clouded sky. Their sense of time would be narrower, their imagination less drawn to vastness. Perhaps culture would grow inward, more bound to the immediate, less to cycles and rhythms. Or picture the opposite, a world with skies even clearer than ours, where the Milky Way shines so brightly it feels near. In such a world, perhaps humans would have looked outward sooner, reaching for understanding earlier, guided not only by necessity but by awe. In both cases, the cosmos influences not by force but by presence, shaping the paths of thought. We must remain cautious here. Culture leaves traces, but interpretation is delicate. We cannot know exactly how much the stars guided human evolution compared to rivers, forests, or plains. Yet the constancy of the sky, shared across every generation, suggests its role was profound, even if subtle. It gave us a mirror in which to see ourselves, a backdrop against which questions could grow. Now we soften into perspective. To speak of evolution is to speak not only of survival but of meaning. The cosmos, in its silence, may have offered us both. It shaped the environment in which life unfolded, but also the minds that learned to wonder. Whether through radiation, impacts, or quiet inspiration, the universe has always been part of us. To recognize this is to let the story remain open, unfinished, stretching into time yet to come. We let this thought settle gently, like the final chord of a song that does not end but fades, leaving space for silence, for breath, and for whatever comes next. And if this rhythm feels close to us, we already know how to return, to listen again, and to keep walking with the story.